Kia ora tātou, it's Bill. I want to have a look at resolution for an ADC. And typically we talk about resolution in terms of the number of bits. So for instance, the AVR resolution, the ADC has a 10-bit ADC, so we say it's a 10-bit resolution. But I also want to discuss how we talk about voltage resolution. And voltage resolution is that sort of minimum voltage that needs to change on the input of the ADC to move one bit of this. So we calculate that by looking at our input voltage range. So in our case, our reference voltage range, which is VCC, and we divide that by 2 to the power of n, which is the number of bits. So of course, then what we get is we've got, say, 4.8 volts coming in, and we've got 1024 is our range. So our resolution works out to be around about 5 millivolts. So that's 4.8. I'm just doing this on my calculator on the screen. There we go. 4.7 millivolts. So what that means is that we should be able to change the voltage from our potentiometer by about 3 millivolts and not see a change in our output number appearing up here in the terminal. So let's just see if that happens. So what I'm going to do is I'm going to put my little tiny adjuster in there, and I'm at 511 at the moment, and I'm just going, well actually let's just record this. What voltage we got? 2.44. So I've already flicked over to 12 by just adjusting it. It's a little bit unstable. It's really hard to measure the voltage resolution with something like a cheap trim pot like this, and also the amount of noise in our power supply. Also, we don't have the capacitor on our reference voltage, so it's going to be a little bit difficult to see this, but we should be able to see there's a little bit of change, about 5 millivolts change when we adjust each step in this. So 2.443, let's try, I'm sitting on 517 at the moment. I'm going to change that to, it's really jumping around. It's really quite hard to see. 2.47 something, 2. And if I take this to 518, 2.48. So we are seeing a bit of change there. It's a little bit difficult. You know, we really don't have the accuracy. Looking up here in our voltmeter, you can see that we're jumping around just a little bit. And also here, we're on the cusp of changes all the time. It's really hard with this cheap potentiometer. And the reason is that inside these is a very simple little mechanism, which has got a lot of play or backlash in it. So what we can say, though, at the moment is we've got about 5 millivolts voltage resolution. So for every change of 5 millivolts on our input, we're going to take another bit step in the output. Now, the ADC on this is 10-bit, and it's limited to a number of conversions per second. If we look over here, it's limited to about 15,000 samples per second at our maximum resolution. There's an option to change the resolution in this ADC, and that's using something called ADLAR. And we'll find ADLAR in one of these registers. So there's ADLAR, it's in the ADMUX register. And what the ADLAR bit does is it affects the presentation of the ADC conversion result in the ADC data register. So what we've got in the AVR is a data register which is actually 16 bits wide, and it's made up of 2 halves: ADCL, ADCH for high, and overall we call it ADCW. W doesn't actually exist, it's just a macro inside the software. So if I look at my software, I can see that this return ADCW is actually returning a 16-bit number, which has been put together from ADCL and ADCH. Back to my data sheet. So looking at this, it says for a complete description, see ADCL and ADCH, and I click on that, and this shows you what's happening. So at the moment, when ADLAR is 0, we're returning these 8 bits of data here. So we're returning these 8 bits of data, and we're ignoring these 6 bits of data here. And when we set that to edlar bit to 1, what's happening is, instead of returning this, we've got, here's our ADC high and ADC low. This bit here is translated up here. So we're actually returning these bits here. And these 2 bits here are lost, and these are replaced with just zeros. There we go. So we can have a look at this in the software. Let's see what happens. At the moment, we've got a number around about 520, which is on our range of 1023. But if I go back to my code and I decide to set this bit edlar, what I'm going to do is program that in. And there we go. Now what we're seeing here is we're seeing both registers together. So I'm looking at both registers, which is why these are all 0. We lose these 2 bits off the end. They're no longer there. And we get 6 zeros on the end. So let's just have a look at that. Our last bits are 0. Well, in actual fact, they're not 0 if you look at it. We can adjust it so that those bits are actually there. And we can see them. So at the moment, I'm seeing that those bits are actually being set. So we do right adjust it. Let's just see what it says in the data sheet. It says that those 2 bits are there. Now we can ignore those if we want to and just read ADCH in our software. So let's just read ADCH instead of ADCW. And I'll just program that in now. There we go. And now we're ignoring. Now, actually, I want to just pause this for a second if I can and have a close look at what happened in this line here. This is something that you need to be familiar with. Whenever you're doing your first conversion with an ADC, the first value will generally be wrong. And that's when I reprogrammed this. And so instead of reading 145, it read 81. And you'll find that the first conversion you do, and it talks about this in the data sheet, is often wrong. And so you need to ignore it. Okay, I'll just let that go. And there's our conversions coming through. And of course, now we're no longer looking at all 10 bits, we're only looking at 8 bits, so this will max out at 255. And just adjusting that, I've got that to 255. That's the maximum value that we can get. Cool. Now I'm just going to set these back again to look at my 10-bit number, and I'll program that in. So now we're going back to our 10-bit number. There we go, 1023. Now, what if, for instance, we wanted to do say we only wanted a 3-bit number? And that's what I've done here with these 3 LEDs. So as I reduce this down, you can see that my 3 LEDs are just counting the top 3 bits. So at the moment, my top 3 bits are 101, and my LEDs are showing 101. So what I've done to do that and just get a 3-bit number is when I've read the ADC, I'm using this show count function, which we've used previously before, which is just to show a value from 0 to 7 on the LEDs. And what I'm doing is I'm sending that function a value, the value which is being read, and I've shifted it right by 7. So now I'm back in my 10-bit mode, and I've got this number here, and I'm shifting it 7 bits to the end and passing that to my function, which of course what the function does then is it clears those 3 bits, shifts the value to the right by 1, and then writes them into those bits. So that's how I'm getting a 3-bit resolution, and you can see that my system now requires a significant change in voltage, and the voltage resolution for this is quite different. So if I set this to say, well, there's 100, and I'll just get this so it just clicks over into if you look at the rest of the numbers, you can see it's going to jump into 101 in a little bit, getting close to 101. There we go. We've just gone to 101. So that's at 640. So a count of 640 is actually 1, 1, is 1, 0. Now it's just hovering there a little bit. I need to just make that, it should be, again, the little backlash and play in this little mechanism is not strong. It's not good for us. There we go, 101, and the rest are all zeros. And the voltage at this point, which is causing this, is 3.037 volts. Now what I'm going to do is I'm going to increase this until I get to 110, the next count in our 3-bit ADC. So 110, watching the rest of those numbers as they come up to find where I get to 110. There we go, we're at 110. Just hovering at that point, which is 768. So 768 is 110. So in a 3-bit number, we've gone from 5 to 6. Our full range for 3-bit, of course, is 0 to 7. And the voltage now, when we're on 768, is around 3.64 volts, which is a range of literally about 6 volts per step. Now, if we do our calculation for voltage resolution, which of course is VCC or VREF, as they're connected together, and we divide that by, sorry, you can't see that. Just go back again. So this was the voltage, 3.604 volts at a count of 6 and 3.3037 volts at a count of 5, a difference of 0.6 volts. And of course, our voltage resolution for our system is our reference voltage over our count, which is 8, which of course is 0.6 volts. So we're seeing 0.6 volts. So our input voltage is changing like this, but our actual ADC values are changing at 0.6 volts intervals. So there's 0.6 volts there. And of course, there are only a number of intervals, which will be from 0, 0, 0 through to 1, 1, 1. Now, that's voltage resolution. Again, you can't see that piece of paper, my apologies. So I'm counting my voltages changing linearly from 0 to 4.8 volts. At each 0.6 volt step, we're going to see a change in the ADC value like this. And our voltage resolution, of course, is 0.6 volts, 4.8 volts over a number of steps, 8. Now, that's voltage resolution. So we've got different options here. If we speed up our microcontroller, we can actually use our 8-bit system only, ignoring the rest of this because it'll be inaccurate. And we can just read those 8 bits and we can actually take more samples per second. And in the data sheet, it mentions that here. So we go back to that. It says that it's 15 kilosamples per second at maximum resolution, but we can get up to 76.9 kilosamples per second if we change that back. Okay, I hope this is a little bit helpful in terms of voltage resolution, seeing these values actually happen on the microcontroller. Cheers.